Hi, everyone. You're with us right now because when we were going through and introducing our angle identities, you got to the point where you looked at this big, ugly compound angle identity and you wanted to know why. Why can I just trust that the cos of a plus b is equal to that expression? So, as we work our way through, this is a proof for that compound angle identity. I will never ask you to duplicate this proof. It's pretty intensive. But this is us going through to ensure that we can understand that if we are given a compound angle, that being an angle that's made up of two smaller angles. So in this case, I would be adding two angles together. We could break it down into their basic angles or their component angles. So we're going to start off, and if you are following along with me on this one, I'm going to recommend that you get down a few colors. So take a moment, pause the video if need be, grab a few colors because we're going to mark up our unit circle pretty good. Okay, pause it now if you need to. Otherwise, we're going to start working our way through to try to deal with this proof. And I'm also going to talk to you about it in terms of if you were to produce this proof on your own. Again, I have to reiterate, I'm never going to ask you to do that on an evaluation. But I would hope that we would be looking at, like, how could I prove this on my own? Okay, I'm just going to get rid of all of those underlines because when we look at that property, that identity at the top, for us to prove it, we have to see what we're being asked to prove. So we are being asked to prove that the cos of an angle plus an angle is equal to properties that are based on the individual angles. Okay, so that means that if I was going to do a geometric proof for this, I need to somehow get on my diagram, at least my goal, the blue angle, A plus B, as well as the individual angles of A and B. Okay, so let's just start it off then, and we'll build some stuff kind of small, slowly. Again, I'm just going to get rid of all those markings in the original theorem. Okay, what I'm going to do first is, similar to our other angles, I'm going to go through and I'm going to draw on one of my angles. And I'm going to put on A, just because A came first. Now, there are times when you want to be very careful not to draw A like it has any specific property. In this case, I don't really mind. I'm going to put on A. And even though it might look like A is a pi by 4 angle or a 45-degree angle, it has no intention to be that. It can be anything, and I'm just going to put it in quadrant 1 to make our diagram look a little more straightforward. Let's imagine that that terminal arm we just rotated is going to hit our unit circle at a point M. And we should be good then that point M would have to lie at a location of cos A, sine A. Okay, now what's different in this problem is we're going to need to have an A plus B angle in there. So that means that I'm going to have to produce a terminal arm that lies in a position based on me rotating an A angle and then a B angle. So what I'm going to do is I'm now going to rotate some imagined amount of B angle from A. Now, for the purpose of this proof and making sure that our diagram can look a little cleaner, I'll explain it later. When I rotate B units, whatever that is, from the terminal arm A, I want to make sure that I don't put it at a, let me just get my blue down here, that I put that at what looks like I just rotated pi by 2 or 90 degrees from A. It's not like I can't. I totally can. I just think that we're not going to see a relationship because of what we're about to do. So my recommendation to you would be, I'm going to draw an acute angle for B. So it's going to be a little bit bigger than what I need to get into quadrant 2. but it's clearly not going to get to the middle. Again, I'll explain in a moment why that might make your diagram a little easier to understand. Okay, so what that just was now was me rotating B from A. So if it helps, I'm just going to put the arrow on as well for angle A. I hope that we can see that if my terminal arm was laying in the position of the blue terminal arm, I would have rotated A plus B units. Okay, now that we're in that position, let's also label the coordinates of where that would intersect our unit circle. Now I'm going to have some uglier coordinates, so you're going to see me call this point N, and look where I put the N. It's all the way out there. Because the coordinates of that point would now be cos A plus B and sine A plus B. Pretty ugly coordinates. Now, I want to take a moment and I want to explain why you may have a little bit of hesitation there. Notice before, when we went and we proved some of our other theorems, like specifically our negative angle theorem, that we would have then been able to say, yeah, but that's in like quadrant 2, so shouldn't my cos coordinate be negative? And here's where we need to stop. I can't say for certain that point N is in quadrant 2. Remember, I need this to be as generic as possible. Like maybe angle A was so big and angle B was so big that if I actually added the two of them together, that should have put you in quadrant 4. Well, then your x-coordinate should be positive, not negative. So what I need to do then is I need to just keep that blue point labeled as generically as possible. So the x-coordinate is cos A plus B. And when we calculate the cos of that angle, when we know it, if it happens to be negative, then we would have that terminal arm lie in the correct position. Everything the same for the y-coordinate. So by keeping it just as cos A plus B, sine A plus B, I am keeping it as generic as possible, and therefore I haven't put in any specifics. I'm going to prove the theorem as it's stated. Okay, we got to that point, and it's okay if you have no clue on where you think we're going. I want to draw back up to the theorem, though, so I want you to take a look at the theorem. And I want you to notice that what we have on our diagram includes 2 of the 3 parts. Like what I have is, I have an angle A. Sorry. And I have an angle A plus B. My problem is, I don't really have an angle B. Now, you look at the diagram and I have an angle B, but I don't have an angle B from standard position. So I'm missing an angle B. So what I'm going to do is I'm going to put on an angle B. Now, as you take a look at that angle B, I think you could see that if I was to go and put that into into quadrant 1, my diagram is going to get really confusing. So I actually have another way to put on an angle B. Now, some of you might look at this and you might say, Gray, I think you're like fudging it. And I am not fudging my diagram whatsoever. But I am coming up with maybe a smart way to go through and put on an angle B while keeping my diagram nice and orderly. What I'm going to do is I'm actually going to rotate down B units. So I'm going to try to estimate that whatever size angle I created to produce my blue angle B, I'm going to now rotate as a negative angle B. So I'm doing my best to estimate it. Like I am eyeballing it, and I think that I am going to get there. That is my eyeballing it. And me rotating negative B units. Notice, I did rotate B units, I just did it in a different direction. So I have included an angle of size B on my diagram. Okay, I can label that point, and I'm going to label that point Q. And now I can label on the most generic coordinates I can. Cos of the angle is my x-coordinate. Sine of the angle is my y-coordinate. And everything is the same as what was stated before about point N. I can't label my y-coordinate as negative because maybe angle B was so big it should have put me up into quadrant 2 or quadrant 1. Okay, what I have on my diagram is almost everything I need. I need 2 other points labeled, but the nice part is they're not points that I need to draw. The first thing I'd like you to do is, can we label our origin O? And I'll just call it O for origin. I don't care what label you give it. And what we're also going to do is we're going to label where our unit circle hits our x-axis, specifically our positive x-axis. And we're going to call that point P because we actually know the coordinates of point P. Since it is our unit circle, then we are 1 unit to the right. Okay, that's almost everything I need on my diagram. Now all I'm going to do is I'm going to put some stuff together. What you're going to see me do, first off, is connect point N with point P. Now, you may be saying, okay, why is he doing this? But I want you to notice what happens as soon as I connect point N with point P. Can you see, and I'm just going to highlight in here, that I have now created a triangle. I'm going to get rid of those highlights so you can see it highlighted. Okay, can you see triangle NPO? And more importantly, what is the angle inside that triangle? We have an angle of A plus B. And if we look back up into our proof, we have to prove something about an angle with A plus B. So what I just did was I created a triangle that contains the angle I need. Well, if I go and I do the same thing, I create another triangle. And now what I'm going to do is I'm going to connect point M with point Q. Oh, and I got my highlighter on again. Well, now if I connect point M with point Q, we should see that we have another triangle that's built. And just as important, look what angle we have contained on the inside. Notice that that is angle A plus B. It's angle A as I move from my positive x-axis into quadrant 1, and then add to that angle B as I move into the 4th quadrant. Now, some people may be able to look at those diagrams and understand the importance I have. I'm going to write down exactly what we just found because it is huge. That triangle NPO, and you may recognize that symbol, as compared with triangle MQO. I'm hoping you recognize that blue symbol, although you probably haven't seen it in a while. That's our statement for congruent. That we should be able to see that triangle NPO and triangle MQO are congruent, which means they are the exact same triangle. Same angles, same side lengths. Now, if we are struggling to see that, here's our proof. I want you to focus in on triangle NPO. First off, we should be good that we have angle A plus B. We've already stated that. But I also want us to notice that that terminal arm that put us up to point N has a length of 1. And I'm just going to draw on the terminal arm that put us out to point P. Because we're on our axis and we didn't draw a terminal arm because we technically didn't rotate it, that's also a length of 1. And so I hope that we could see that we actually have side angle side on that triangle to create the length of NP, whatever that is. We could use cosine law, and we could find the opposite side to angle A plus B using those side lengths. Okay, well, can I get you to take a look now at triangle MQO? And notice the triangle MQO is the same. We've already addressed that it has angle A plus B on the inside, but also the length of M is 1 and the length of the terminal arm to Q is 1. I want us to see that we actually have the same triangle. So just as a small little kind of nerdy point on my part, take a look at your diagram and just see like how close do the two triangles look to being the same size. The only reason I ask is you did an outstanding estimating job if they do look the same. And I have to tell you, I am pretty proud of the way those look. That might be my best job estimating ever. Normally, they're way off. Okay, I'm going to get rid of all of that other notation that we just put on to go back to our original triangle. Okay, let's get back to our statement at the bottom then. The triangle NPO is congruent to triangle MQO. Why is that important then? Because it allows us to draw this most important conclusion. That the length of NP has to be exactly the same as the length of MQ. And so what we can do then is we can examine the length of NP and the length of MQ, and we can set them equal, and we can see where that takes us. Okay, I'm going to jump onto a separate screen. You already have this diagram. So what we're going to do is we're going to take that statement of NP having to equal MQ, and we're going to run with it. Okay, here we go. If I know that NP, sorry, that's really high there, that NP is equal to MQ, then I can create the lengths of line segments. Now, maybe you remember back to grade 10 and you learned a big, long length of a line segment formula, or maybe you just recognize it as Pythagorean theorem. But maybe we recognize that as the length of a line segment formula. Subtract your x values, square it, subtract your y values, square it, take the square root of the whole thing. What we're going to do is we're going to use that formula, that relationship, to determine the length of NP and MQ. Okay, here we go. So NP now has to be the square root of... Okay, I'm going to take the x-coordinate at n and subtract the x-coordinate at p, square it, plus the y-coordinate at n, subtract the y-coordinate at p, square it. Okay, maybe you can see how small I'm writing this because this is really going to fill up the page quickly. That's equal to now the square root of, and now I can come up with the length of m. Okay, so I have the x-coordinate at m minus the x-coordinate at q squared plus the y-coordinate at m minus the y-coordinate at q squared. So what you have is really all the work. There's your problem solving, the diagram, and getting down to that blue. The rest of it now is just our algebra, and then just being able to kind of draw from some things from the past. So what I'm going to do is I'm going to now try to simplify that expression and manipulate the way it looks to try to simplify it and express the idea in an easier way. Let's see what relationships we might be able to find in there. Okay, first off, I would hope that we are all good, that we could just square both sides of that equation and we can get rid of those big ugly roots. So let's square both sides. At the same time, what I'm going to do is I'm going to expand all my brackets and collect like terms and see what I have. Okay, I'm going to write really, really small because this is going to become a very long equation. And I'm going to try my best to fit everything on this screen. You can clearly zoom in, zoom out if you need to be able to see. Okay, here we go. So square the first. So I need to square my cos A plus B, multiply them together, and double it. Square the last. Now, square my next. Well, the nice thing is sine A plus B minus 0 is really just one term. So I can square my sine A plus B. Okay, no joke, I might be writing too big to fit in this next side. Okay, I'm going to do my best. Now I need to square the next bracket. So, square the first, multiply them together and double it. Square the last. And now square the last bracket. Multiply them together, double it, and square the last. Oh, it looks like I'm going to fit it on. Nice. Oh my goodness. Okay, I'm going to keep alternating colors so we can just tell one line apart from the other a little easily. Okay, when I take a look at that line, now I want to try to go through and clean up as much stuff as I can. My problem is I look at that next line and I don't have any like terms. So there isn't anything that I can clean up. Just take a peek. I have A plus B angle, but it has a cos squared. Then I have an A plus B angle, but just a cos, so I can't collect those. I've got the same problem with my sine. Now, all of a sudden, on the right side, I just have individual angles. So I don't even have the ability to have like angles, so therefore I can't collect. Okay, I'm going to get rid of all of that purple. So if I can't collect, then what I need to try to do is manipulate the expression. Okay, well, the first thing I notice is back in my original theorem, I don't have any negative angles. So if I don't have negative angles in there, then I'm going to eliminate my negative angles here. And notice what we have is we have the negative angle of B. So what I'm going to do is I'm going to use one of my negative angle identities to go through and remove those negative angles and change them to positives. So I look and I go, well, there's a cos of a negative angle. Oh, and I also have a sine of a negative angle. So I've got coses and sines of negative angles. I'm going to use those two identities. So I know that the sine of any negative angle is equal to the negative sine of the positive. I'm going to use that one. I also know that the cos of any negative angle is equal to the cos of the positive angle. So I'm going to sub that in to my expression. Okay, what we're also going to do though, let's clean up some other stuff. If you take a look, you notice that you have cos squareds and sine squareds. And then on the right side, you have like a cos squared, a sine squared, and a sine squared. And as soon as I see cos squareds and sine squareds, I'm hoping that something from your grade 11 course is popping up. That we also know that we have our Pythagorean identity, that sine squared of some angle plus cos squared of some angle equals 1, as long as those angles are the same. So I'm going to see if I can use my Pythagorean identity to sub in as well. Okay, we got a lot of stuff here. Okay, here we go. Well, there is a cos squared a plus b. So I want to scan across and find another angle, hoping for a sine squared a plus b. And I've got it right there. They're both positive. So if I was to put those two ratios together, then they're going to equal a value of 1. So I could sub in 1 for those two values. So I'm going to replace them with a 1. They're gone. That means on the left side, I still have this cos a plus b and the other plus 1. Okay, let's scan on the right side. Well, I have this cos squared a, and if I go all the way down here, then I notice that I have a positive sine squared a. So I have a sine squared a plus cos squared a. I know that that gives me 1. But that wasn't the only instance. Notice I have a cos squared negative b. And if I scan all the way down to the end, I have a positive sine squared negative b. So I've got another cos squared plus sine squared of the same angle. I have another 1. So I can add those in. Okay, now I have my two other terms. And within those two other terms, I have my negative angle. So what I'm going to do is I'm going to use those purple negative angle identities to sub in. Okay. In the first one, I have a negative 2 cos a cos negative b, but I know that the cos of a negative angle is equal to the cos of a positive angle, so I can get rid of the cos negative b and replace it with a cos positive b. That term is now taken care of. And I've got my last term. So now I have my minus 2 sine a sine negative b, but I know that the sine of a negative angle is equal to negative sine of a positive, so I can get rid of that sine negative b and change it to a sine positive b if I change the sign of my term. And that's why it became a positive. Okay, we just did a ton of work there. A ton of work. Every time we use an identity and we sub it in, our next action is taken for us. Now we simplify. So let's collect whatever we can on both sides. So on the left side, I'm going to get a 2 minus sine. Ooh, I don't even know why that was a sine. A cos a plus b. There's my left side simplified. My right side, well, all I can do is put together my 1s. And I have no idea why I keep writing down sine. How about cos a cos b plus 2 sine a sine b. Okay. Well, I can subtract a 2 off of both sides. Those will cancel out. That's nice. That at least gets me down to a negative cos a plus b equals a negative 2 cos a cos b plus 2 sine a sine b. So I'm getting to there. Well, now I take a look. I have a common factor of 2 on both sides. Now, I'm not going to blindly just divide out a 2 because I also notice if I look back at my original identity was about cos a plus b. So I actually want to get rid of that whole negative 2 out in front. So what I'm going to do is divide out both sides by negative 2. And when I divide the left side by negative 2, I get cos a plus b. And when I divide the right side by negative 2, This first term becomes cos A, cos B. And the second term is going to change signs to a sine A, sine B. And wow, there it is. Whew. Okay, we actually got down to proving that identity. Now, as we get going, by no means should you be automatically going, okay, I fully understand what we just did now, and I understand the importance of it. No. I would hope that we are good with the entire proof, that we can see how we built our diagram and why, to incorporate the compound angle as well as the individual angles. I would hope that we're good with our statement that those two triangles are congruent. And I would absolutely hope that we are good with everything you see on the current screen. That's us using length of a line segment, some grade 11 identity, some grade 12 new identities, and all of our algebra skills to be able to go through and prove that the cos of A plus B is equal to cos A cos B minus sine A sine B. Okay, if you were able to hang in there, well done. We won't really see where it's useful for another little bit, but I'm telling you, we just found a super useful tool, and pretty quickly we are about to kind of blow off the doors in terms of our theoretical trigonometry. Well done. Okay, I'm glad you enjoyed. I'm hoping you enjoyed the video, and I'm hoping that you were working your way through all those proofs. Take the time off, make sure that you are good with those identities, but when you come into next lesson, you want to have them cold. Okay, good luck.